Good afternoon, everyone. My name is Lucian, and I will be your tutor for today. Okay, just by a show of hands, just give me a thumbs up if you can hear me and see my screen shared. Those guys on Teams. Okay, thank you, Mr. Dube, Mr. Bisa, and I apologize if I mispronounce your name. And then, of course, we have also the Mr. Tabiso. Okay, now, guys, today we'll be doing, first of all, before I begin with these problems based on uh, conservation of energy, do you guys have any questions regarding the work you've done so far? Any problems at all? Anything you may struggle with? If you have, just let me know. And I seem to be right as usual. Okay, let me just try to figure out what is happening with my camera now. Okay. Okay, if there are no questions, then I will continue. Okay. And there's this annoying light at the back of the screen. Okay, that should be good enough. Yes, that's it. Okay, if there are no questions, let me just check something out. Maybe there are some questions on YouTube. None. Okay, no questions. Okay, now if since there are no questions, I'm gonna start, and there might be a bit of lag due to the rough winds that we are experiencing here, and I've often found that these winds are detrimental to uh, Mr. Kelvin. You asked if this session is for civil engineering students. Are you studying PHYV or FVV? I am assuming PHYV. Okay, if you are studying PHYV physics, then yes, this session is for you. This session is for both for FVV and PHYV students. Okay, did I answer your question, Mr. Calvin? I assume it's Mr. Hello, Calvin. Did I answer your question before I continue? Okay, cool. Thank you. Now, this is for if your lecturer is either Prof. Olivir or if your lecturer is Dr. Waswa, then yes, the session is for you. Okay. Hmm. So let me just start. We're going to be doing some problems on conservation of energy. Okay. So tutorial number 4. Yeah, just get that. Part 4. It's going to be based on conservation of energy. Okay. For those of you who don't know, there's a universal law which states that energy cannot be created nor destroyed. it can just change its shape, okay, or its format. And in 1905, a scientist, which you all should know, I think, Albert Einstein proved that even mass itself is a different form of energy, okay, and that they then related the two previously disjoint concepts of mass and energy by the equation E equals mc squared. Okay, so everything in this world is energy. If mass is
Incredibile. Grande. Della...
Mr. Tabisa, your mic is on. Uh, okay, so everything in this world, the amount of energy in this universe is always the same. Okay, okay, it can just change its form and its shape, but it does not decrease. It neither decreases nor increases. Okay, energy is always conserved. Whether you can use that energy is a different question. Okay, now let's go to some questions revolving around the conservation of energy. Okay, and how we calculate energy and work. Okay, work and heat are two forms of energy. Okay? Two forms of energy in motion. Okay, now a shopper, let's say question one, a shopper in a supermarket pushes a cart with a force of 35 newtons directed at an angle of 25 degrees below the horizontal. Okay? The force is just sufficient to balance various friction forces so the cart moves at constant speed. So we have this cart. Okay, I'm going to give a terrible drawing now. So we have this cart. It's pushed by the shopper. Okay, and the shopper pushes it with a force of 35 newtons, so a force of 35 newtons at an angle of 25 degrees below the horizontal, so 25 degrees below the horizontal. Okay, so below the horizontal. So this is what's happening. Sorry, that's a 35 degrees below the horizontal. Okay, so a shopper pushes the cart. So let's say in this direction, the cart is moving in this direction as the shopper is pushing it. Okay, now this force, they tell us, is just sufficient to balance the various friction forces so the cart moves at a constant speed, meaning that if this cart is moving at a constant speed, that the sum of the forces, the sum of the forces will be equal if net, the sum of the net force is equal to zero. Okay, so the sum of the forces is equal to zero, or F net is zero. The net force is zero. There's no net force because it's not accelerating. Okay, we can say the sum of the forces, I don't need this actually, the sum of the forces is equal to zero because there is no net force. The forces are equally balanced. Okay, now the first part of question number one asks, okay, let's say this cart, okay, I'm gonna read the question as it is. Find the work done by the shopper on the cart as she moves down a 50-meter long aisle. Okay, so the work done by a 35 Newton force at an angle of 25 degrees. Also, that's the horizontal, so that's also going to be 25 at an angle of 25 degrees. Find the net work done by that force. Okay, now the work done by the shopper, so the work done by the shopper is equal to the force applied by the shopper So it's the force applied by the shopper multiplied by the distance that the force is applied. Okay, along which the force is applied. Okay, so the force applied, remember, we are not talking about the force applied at 25 degrees. We are talking about the force in the same direction or in the exact opposite direction as the motion. Okay, so it's going to be the horizontal component of this 35 Newton force. Okay, the horizontal component of this 35 Newton force. So let's see. So it's going to be 35 newtons multiplied by, and this force has a horizontal component, which we're going to work out as the cos of 25 degrees multiplied by that 35 newtons will give us the horizontal component of this force, and it is applied over a distance of 50 meters. Okay, and that, ladies and gentlemen, gives us a work or done of 1.59 times 10 to the 3 joules, or you can write it as 1.59 kilojoules. Okay, so 1.59 kilojoules of work is being done by the shopper. Okay, so 1.59 kilojoules of work is being done by the shopper. Okay, are there any questions? Okay, I'm going to go to the Teams app and to see if there are any questions. Any questions from your side? Anyone, any questions? Is it clear? Mr. Yanela, is it clear? Mr. Dube, Mr. Tabiso, Ms. Balente. Okay, seems clear to most of you guys. Okay, good. Mr. Bisa, I missed you there. Okay, so the work done by the shopper is 1.59 kilojoules. Okay, the next question asks, the shopper goes down the next aisle. So this is in one aisle. Now the shopper goes down the next aisle. Okay, pushing horizontally. Okay, she's no longer pushing at an angle of 25 degrees. She's now pushing horizontally. So that 35 Newton, all of it is now applied horizontally. Okay, so the shopper goes down the next aisle pushing horizontally and maintaining the same speed as before. Okay, if the friction force doesn't change, would the shopper's applied force be larger, smaller, or the same? Okay. There's Mr. M. Mit. Okay, so the shopper goes down the next aisle, pushing horizontally and maintaining the same speed as before. Miss Philippa Robinson, Mr. M, welcome. Okay, we are doing this problem on a shopper pushing a cart. Okay, so the second part of this problem is the shopper is now walking in another aisle, pushing this cart horizontally and maintaining the same speed as before. Okay, so same constant speed. So still no net force. If the friction force doesn't change, would the shopper's applied force be larger, smaller, or the same? First of all, let's see. They say the friction force doesn't change. Now, friction is dependent on, let's reason this out. The friction force doesn't change. If friction force doesn't change, would the shopper's applied force be larger, smaller, or the same? Let's look at the applied force. Okay. Now, because there's no vertical, remember originally the force acted at an angle of 25 degrees. Okay. Now they're saying, this is in part 1 of the problem. Now in part 2 of the problem, the force is now horizontal. Okay. Now they're saying, since there is no vertical component, this one has no vertical component. No vertical component. This force has no vertical component. Since there's no vertical component to the second force, well, not the second force, the force in part 2, okay? Since there's no vertical component, it means that the normal force is less. Okay, the normal force is less. Okay, there's no vertical component, so no vertical component. There's no vertical component. That means there is the normal force. The normal force is less. The normal force goes down if there's no vertical component. Remember, the normal force must balance all the forces in the coming downwards. Remember, if there was a vertical component, originally in part 1, there was a vertical component for that force, and it pushed down together with the weight of the trolley on the way on the ground. Okay, and the normal force had to counteract that force. Okay, but now there's no normal. Now there's no vertical component. There's only the cart's weight pushing downwards. So now the normal force is less. Okay, and if the normal force is less, if the normal force is less, if the normal force goes down, if the normal force goes down, friction goes down. Friction goes down. They say there the friction force doesn't change. It does. Okay, it cannot stay the same because the normal force has changed. So if the normal force goes down, the friction force goes down because friction is equal to the the friction force is equal to the normal force multiplied by the coefficient of friction. Okay. Now the coefficient of friction is a constant for the type of material which the floor is made of. Okay. So if the friction, if the normal force goes down, remember, I'm just going to write it here on the side. Friction is equal to the normal force multiplied by the coefficient of static or either kinetic friction. Okay. Now if the normal force goes down, then the friction must go down. And if the friction goes down, but the speed is still the same, if the friction goes down, but the speed is still the same, therefore, if the friction goes down, then the applied force, if the friction goes down, then the applied force goes down. Okay? So the applied force goes down. The applied force. Does that make sense? Does that make sense to one of you guys in the Teams meeting? Can you just, by way of indicating, just tell me if that makes sense to you guys? Oh, Cello, I see you asked the question. It's not a problem if you write it as a normal number. You don't have to write it as scientific notation. You can write it as a normal number. Unless it's too big, then usually we just go for scientific notation. Okay. Uh, Let me now flip. I'm balancing. I'm between two screens here. Someone in team, sorry, I was not looking at the team screen at the moment. Is there one person that doesn't understand? Everyone with me? By show of hands, who understands what happened? Why the applied force is now less? Okay. Superstition. Thank you, Miss. Okay. Now, if the applied force now is less, okay, because we've shown now that the normal force is less, meaning friction force is less, the friction is less, and if the friction is less, then the applied force is less to still balance out. If the friction is less, then the applied force must be less if we're still moving at the same speed, meaning that it still don't net work. And there we have it. The first one, the answer is 1.59 times 10 to the 3 joules, which we got earlier on. And then the second one, the applied force is now smaller than before. Okay. Now, the third part of this question, number three, third part of this question, what about the work done on the card? If the applied force is less, will the work, what happens to the work done? Okay, the applied force is now less. Remember, work is equal to the force applied by the lady times, or dotted with, the distance over which this force acts. Okay, so that is then if the apply, so work is directly proportional to the force applied. Okay, so if the force applied goes down, then the work must go down, so the work will be less, or the work will be smaller. This, the work cannot stay the same. Here they say that the work is the same. That is not correct. The work is not the same, because if the applied force is less, then the work must be less. The applied force is less, meaning the work is now less. Okay, just ignore that. Work is the same. The work over the same distance is the same. The distance is the same, they tell us that, but they then, in the previous question, we worked out that the force is less, and if the force is less, then the work done must be less as well, because force and work are directly proportional in this case. And we are only calculating the work for that particular force, the force applied. Okay. Remember, we are working with energy, how to calculate work. Okay. Now we are moving to question number 2. I'm going to give you guys a breather for about 20 seconds. If you have any questions, just ask. Okay, let's see. A block, question number 2. A block of mass. Let me just draw the situation. So we have a block. It is of mass m 2.5 kilos. So this block is 2.50 kilograms. Let me just draw it bigger. So question number 2, we have a block. It is 2.50 kilograms. and this block is pushed a distance of 2.2 meters, so from the center right there. So this block is pushed 2.2, a distance of 2.20 meters along a frictionless, so there's no force of friction, by a constant applied force of magnitude F 60 newtons. So a force of 60 newtons directed at an angle 25 degrees below the horizontal as shown in the figure. Okay, now I don't have the figure in this question, but the force is applied at this angle. So we have the block, we have the force applied at an angle of 25 degrees. This is the force being applied. This force is equal to 60 Newton. Now they want us, and this block is pushed a distance of 220 Newton. So this block is 2.50 kgs, and the same block is then moved, pushed this distance. Okay, it is moved that way. Now determine the work done on the block by the applied force. Okay, so let's go ahead and calculate for number one, the work done on the block by the applied force. Okay, so the work done on block. So because the block can also do work, so the work done on the block is equal to the force that's being applied multiplied by the distance over which that force is being applied. Okay, so the force applied, in this case the force is being applied at an angle. Okay, so the force being applied is 16 newtons, 16.0 newtons, but that force is being applied at an angle of 25 degrees to the horizontal. So to get the horizontal component, we work out the cosine of 25 degrees. That will give you the horizontal component of the 16 Newton force, and it's being applied over a distance of 2.20 meters. Okay, that will give you your work. Okay, and that is equal to 31.9 joules. Okay, 31.9 joules. If you work it out, it's equal to 31.9 joules. So the work done by that force is 31.9 joules. The second part of the problem is they want us the normal force exerted by the table. They want us to calculate the normal force exerted by the table. Okay? Now the normal force, they don't want us to calculate the normal force, they want us to calculate the work done on the block by number one, the applied force, the work done on the block by number two, the normal force. Now, what's the one thing you know about the normal force? It acts vertically at the normal force on this block. Since this block is not on an incline, the normal force will act directly downwards at an angle of 90 degrees. Okay, this normal force will act at an angle of 90 degrees. The normal force acts at an angle of 90 degrees. So let's calculate the work done by the normal force. Okay, now most of you can already know work done by normal force. Okay, you don't need to write this in, I just write this in. The work done by the normal force is equal to the normal force, which is N, multiplied by the distance over which it's applied. Now, This is going to be n multiplied by the distance times the cosine of 90 degrees. Now the cosine of 90 degrees is 0, so the work done by the normal force is 0 joules. Okay, a force acting horizontally to the distance, to the displacement, will always be 0 joules. The work done by a force acting at 90 degrees will always be 0 joules. Okay, number 3. Question number 3, the work done by the gravitational force. Now in this case, the gravitational force is also working. By the way, sorry, this is not the normal force here. The normal force is going up. The arrow should go up, and then the gravitational force should go down. The force of gravity is going down and the normal force is going up. Okay, and they both act at 90 degrees. Okay, now the gravitational force is also acting at 90 degrees, but it is going downwards. Okay, so the same reasoning, the same argument that was used in number 2 can be. So the work done by the gravitational force is also 0 joules because it's acting at an angle of 90 degrees towards the displacement. Okay, question number 4. Let's see. Number 4, the net force on the block. Okay, the net force on the block. Let's calculate the net force, or the net force on the block. The work done by the net force. Okay, so basically we want the net force, the work done by the net force, meaning we want the net work. Okay. In this case, it's easy. Okay, the net force is going to be, the gravitational force and the normal force are going to balance each other out because it's not accelerating upwards or downwards. Okay, meaning there's only one force. It's a frictionless surface, so only the applied force will be doing work. So the net work, the net work, the work done by the net force, the net work is equal to the net force, the net force multiplied by the distance over which this net force is being applied, and that's going to be equal to, the net force is going to be is equal to 16 newtons, and the cosine of that 16 newtons, cosine of 25 degrees multiplied, it's being applied over a distance of 2.2 meters. So the net work being done by the net force is 31.9 joules. Of course, you could have just done this. W net is just equal to the sum of all, or you can say this, W net, meaning the net work, is equal to the work done by the applied force plus the work done by the gravitational force plus the work done by the normal force, is equal to 31.9 joules plus 0 joules plus 0 joules. That is equal to 31.9 joules. So the work done by the net force is 31.9 joules. So let's check. The first answer is 31.9, then it's 0, then zeros, and then the last answer is 31.9 joules. Okay, so we are correct so far in our assumptions and what we have made done so far. If there are any questions, let me know. Give you 20-second breather before we go to the next question. We're not going to do question 3 because somehow this answer is been removed and I can't find it. So question 4 will be the next one, and then 5, then we're done for today. Question 4. Okay, so question 4 has to do with ballistics. Okay, question 4, a 100-gram bullet is fired from a rifle having a barrel that is 0.6 meters long. Okay, choose the origin to be at the location where the bullet begins to move. So while it's still in its magazine, while it's still in the chamber, okay, in the chamber of the gun. That is the origin of the bullet. Okay? Then the force in newtons exerted by the expanding gas on the bullet is, so the force on the bullet is equal to, so the force on the bullet is by the expanding gas is 15,000 plus 10,000 x plus, oh sorry, that's minus 25,000 x squared. So this is the force. Force is written in terms of the distance x. Okay, so the force is written in terms of the distance x, meaning that the force is changing over time. Okay, now the minute that you have that the force is changing over time, you must immediately think calculus. Okay, this is a problem that will require you to use calculus. Okay, now they ask, determine the work done by the gas on the bullet as the bullet travels the length of the barrel. Okay, so the barrel is 0.6 meters long, so we have the distance and we have the force. How do we calculate the work? Okay, so work is equal to the integral from the initial point to the final point, that's of the force, sorry, that's the force of the force dotted with the distance dx. Okay, so the force dotted with the distance dx. Now, the initial point will be our 0 point, and the final point will be the length of the barrel, 0.600 meters. Okay, and then the force we've already been told is 15,000 plus 10,000 x minus 25,000 x squared, and the distance dx. Okay, this is a typical problem involving integral calculus. Now the math department is usually lagging behind, but I assume up this point that Prof. Olivier has taught you the basics of integration. Okay, now the integral of 15x is just 15,000 is just 15,000 x plus the integral of 10,000 x is just 10,000 x squared over 2, and then the integral 25,000 is 25,000 x cubed over 3, and it goes from 0.6 to 0. Okay, or from 0 to 0.6. Okay, now if you plug in 0.6 everywhere and then you plug in minus the whole setup where you plug in 0, you will get the following answer. So thus if you plug in 0.6, you get 9,000 joules plus 1,800 joules for this section minus 1,800 joules for this section. If you plug in 0, it all falls away, but if you plug in 0.6 here, you get 9,000. You plug in here 0.6, you get 1,800. You plug in 0.6, you get 1,800 joules. 1,800 joules. So the answer is 9,000 joules of work is being done, or you can just write it as 9,0 kilojoules of work being done. Okay, now the next question part number 2. Are there any questions? First of all, are there any questions? Unfortunately, you need to know calculus for this part. Okay. If you're having trouble with that, I would advise you to just look up a simple YouTube video or something. But if you still have problem, if you have trouble with it now, this is why I actually give the integrals of these sums, okay, of these problems. I do the whole problem, so you can see what the answer is like. You can then go and check the integral of 15,000 plus 10,000 x minus 25,000 x squared. There are calculators for checking integrals, okay? The law for integration basically, okay, let me just write it down before I go on to the next question, okay? The integral of x to the power of n, so any x to the power of n is equal to x to the n plus 1 over n plus 1. That is how you work out an integral. That's the law. So this is why 15,000 becomes the the there, maybe remember there's an x there, x to the power of 0. So the x to the power of 0 becomes x to the 1 over 1, which is just x. 15,000 stays the same because it's a constant. 10,000 becomes x to the 1 becomes x to the 2 over 2. 10,000 is still a constant. 25,000 becomes x to the 2 becomes x to the 3 over 3. Okay, that's it. That's basically all of it. Okay, the simplest of integration. Now, continuing with number two. But two asks us if the barrel is 1 meters long, how much work is done? So basically the same problem, except now that the distance is changed. The barrel is now not 0.6 meters, now the gun is now longer. Okay? So the work done now is going to be the integral from 0 to 1 from 15,000 plus 10,000 x, that's the force, minus 25,000 x squared dx. Don't forget the differential at the back. If you integrate it, you get 15,000 x plus 10,000 x squared over 2 minus 25,000 x cubed over 3, and then from 1 to 0. That's 1 there, 1.0, 0 to 1.0. Okay, you plug in, then you plug in just 1 for each one of them. So you plug in 15,000 where there's an x, you plug in 1 plus 10,000, you plug in 1 squared over 2 minus 25,000. It is just 1 cubed over 3. So it's 15,000 plus that is just a half of 10,000. That's 5,000. So that's 15,000 plus 20,000 minus. So let me say 15,000 joules plus that's 5,000 minus a third. So 25 divided by 3. Okay, 24 divided by 3 is 6. So 6.3. That's 6.3. So if you subtract 6.3 from, wait, did I calculate that right? That's half 10,000. That's 5,000. It's a third. It's 6.3 thousand. If we subtract it from that, we have 13. Did I calculate this correctly? Let me see. 25,000 divided by 3. Let me just check that. Where's the 0 here? Okay. It's 8,000. Okay, so I was wrong. Not 6,000. 8,333.3. So that multiplied by a minus, that will answer, multiplied by, so you just subtract 8,333 from, so there, what is the others? It's 20,000. So 20,000 minus 8,333.33. So it's 11,600. So the answer is 11,666.67 joules. Or you can write it in scientific notation as 11, or just not even scientific, 11.7 kilojoules. Okay, 11.7 kilojoules, which is what the answer that was given to us, that we should get 11.7 kilojoules. Okay, I hope you all understand how we got there. Question number C. Let's go to C. Let's see number 3. See whatever you choose to be. Okay, so how does this value compare with the work calculated in part 1? Okay, so in part 1 we worked out that the value was 9 kilojoules, but in part 2 the value is 11.7 kilojoules. Okay, so how does it compare? Let's see, let's work it out. So 11.7 kilojoules minus 9 kilojoules, 9 kilojoules over 11.7 kilojoules times 100. That gives us that the answer, that's about 29%. Okay, so the work done is greater by about 29.6%. Sorry, that's 29.6% if you work it out. 2.7 divided by 11.7 will give you about 29.6%. Okay. So the work done by the longer barrel is about 26 point. The work done in part 2 is greater by 29.6%. 29.6%. So the longer barrel resulted in more work being done on the bullet. Okay. Is there anyone with any questions? Oh, Mr. Calvin, thank you. You see, you got the correct answer there. Okay, so question number 5. It is a nice one. Um, Question number 5. The question says, a crate of mass 10 kilogram is pulled up a rough incline. Okay. So a crate of mass 10 kilogram is pulled up a rough incline with an initial speed of 1.5 meters per second. The pulling force is 100 newtons parallel to the incline, which makes an angle of 20.08 degrees with the horizontal. The coefficient of kinetic friction is zero point 0.4 and the crate is pulled 5 meters. Okay, so let's try and draw what is happening here. Okay, let's draw what is happening. So we have a rough incline. Okay, so we have a rough incline. The length, this incline makes an angle of 20.08 degrees with the horizontal. Okay. A crate of 10 kilograms 10 kilograms is being pulled up this incline. Okay. So it's being pulled up this incline. The force applied is equal to 100 newtons. So 100 newtons parallel to the incline. And it has an initial speed, V initial, of 1.5 meters per second. It's good to draw what is happening, that way you understand the problem better. Okay. And then we have a kinetic coefficient of friction of which is equal to 0 0.4 meters, and the distance through which it's being pulled is 5 meters. Okay, meaning the length that it's pulled up is 5 meters. I don't want to draw it in there, otherwise I will clutter it up. Okay, so this is what's happening. This is the situation. They asking number 1, how much work is done by the gravitational force on the crate. Now the gravitational force is acting straight down. Okay, the gravitational force, if this is the, I'm going to draw the free body diagram for the situation where it is just the crate and the gravitational force. Okay, so the gravitational force is going straight down. This is the force that is perpendicular to the horizontal. Okay, that angle there is equal to 20.08, that angle, and this is the right angle triangle. Okay, so this is the opposite side and that is the adjacent side. Okay, this is the, of course, the force of gravity is the hypotenuse. Okay, so they ask us how much work is done by the gravitational force on the crate. So work done is equal to force times the distance. Now the force in this case is just 10 kilograms multiplied by 9,8, and it's working at an angle of, you can work this out for yourself as well. Okay, the gravitational force is working down. If you were to draw, say, a coordinate axis there with 0 degrees there, 90 degrees there, of course this will be 180. You will have here, of course, 270. And gravity is somewhere here. Of course, it is between 270 and 180. Now gravity will be 270. The angle at which it makes will be 270. It's going to, first of all, it's going to be 270 minus that angle which is at 20.08. That gives us an angle of 100 270, that's 100 and another 100 in this case. You can work it out this way as well. That's going to be an angle of 2, what is it, 250, 249.095, 0.95. I'm going to subtract it now, but let me just do the subtraction here. Where's the calculator now? They are all, so it's 270 minus 20.8. 249. Okay, so 249 is the angle from the positive x-axis. Okay. Now, of course, you can also just, yes, Mr. Kelvin, you got the correct answer there. You can also have done the following. You could have just add that to 90 degrees, that value to 90 degrees. Okay, let me just check something before I continue. Clear this. The cosine of 2.49. Don't write this part down. 2.59 negative 0.3 cosine of 110 is also negative 0.3, so it's the same thing. Okay, so remember we are measuring the angle. This is the angle of a gravity. We are measuring from the positive x-axis there. That angle is 220 there. So we subtract that from 270. Okay, so there we have the angles. So now we can work out the actual force. Okay. Yes, Mr. Calvin, that is correct. Okay. At 20.80 to 90 degrees. And then you subtract it from 360, yes. So this is the force, but the force is acting at an angle of, what do we work it out? Cosine of 249. That's the force being used, multiplied by the distance over which it's being used. And that is equal to 5 meters. That gives us an answer of approximately negative 6168 joules. Okay, so gravity does negative work in this case. Okay, this is because the force applied is upwards. Gravity is pulling it downwards. The horizontal component is pulling it downwards. And yes, Mr. Kelvin, you did it correctly. 168.23. Okay, I just wrote 1.68, but yes, you are correct. And then the second part, determine the increase in internal energy of the crate inclined system owing to friction. So by how much does the internal energy of the system increase due to friction? Okay, so due to friction. Now, the sum of the forces in the y direction is equal to the mass times the acceleration in the y direction, and that the sum of the forces is then the normal force, which is going upwards, minus, remember the y direction in this case is that way, so minus the perpendicular component of the force there. It is 98 newtons, which is the gravitational force, multiplied by, and it is the cosine of 20 degrees, 20.08, that should be equal to 0 because this thing is not moving upwards or downwards. So the normal force is thus equal to approximately 92.1 newtons. That is approximately the normal force. Okay, this is force component. I'm not going to spend a lot of time because you've already done this. But if you are stuck, just let me know so I can tell you what to do. Now the force of friction is that equal to the component of the coefficient of friction. Is it kinetic friction? Yes. Multiplied by the normal force, which in this case, the coefficient of kinetic friction is 0.4, multiplied by the normal force, which in this case is 92.1 newtons. So the force of friction is approximately, in this case, 36.8 newtons. So that's the force of friction approximately. Now, if we have the force of friction, we can work out the change in internal energy due to friction. Okay. Now, the change in internal energy due to friction, the change in internal energy due to friction is just the work done by friction. It is just the work done by friction. So in this case, it is just going to be the force times the distance over which the force is being acted upon, is being applied. So it's 36.8 newtons of friction acting over a distance of 5 meters gives us a work of 1800, not 1000, 184 joules. Sorry, 184 joules. So the work done by friction is 18 joules. So our first answer is negative 68 joules. Our second answer is 184 joules. Okay. The third answer, or not the third answer, the third question asks, how much work is done by the 100 Newton force on the crate? So the force pulling it upwards. How much work is done by the force just pulling it upwards on the incline? So how much work is being done by the force pulling it upwards on the incline? Okay. So the work done by the force pulling it upward. Work is equal to force times distance. In this case, or length, whatever. So in this case, let me just make it force times distance for consistency. Now force in this case is 100 newtons because it's parallel to the incline and the distance is 5 meters. So the work is 500 joules. That was reasonably easy. And let's check the answer. Yes, it is indeed 500 joules, the answer. Now number 4. What is the change in kinetic energy of the crate? The change in kinetic energy of the crate. Okay. Number 4, the change in kinetic energy of the crate. Now the change in kinetic energy is equal to the negative of the force of friction times distance. So the work done by the change in kinetic energy is equal to the change in work. Okay, or this. So it's the work done by the force of friction plus the work done by the sum of the work done by the other forces. So the work done by friction. So the sum of the work is equal to the change in kinetic energy. That's the kinetic energy, the work kinetic energy theorem. Okay, so it's the work kinetic energy theorem, the work energy theorem basically. And that is equal to, we have here that the work done, this is just the work done by friction. So it's the work done by friction plus the work done by gravity. Okay, let me just trace it. The work done by friction plus the work done by gravity plus the work done by the applied force. It's the work done by the applied force plus the work done by the normal force. That is the work energy theorem. Now the work done by friction, we just calculated to be 184 joules. The work done by gravity is negative 168 joules. Plus the work done by the applied force of 500 newtons is just 500 joules. And earlier on, we calculated that the work done by the normal force will be 0 joules because it's acting at 90 degrees. Now, if we sum that up, we have that the change in kinetic energy is 148 joules. That's the change in the kinetic energy. Now, we have the change in the kinetic energy to be 148 joules. Number 5, and our last question for today. The question asks the following, okay? What is the speed of the crate after being pulled 5 meters? Okay, so we have the change in kinetic energy. The change in kinetic energy, we just calculated it, is equal to the kinetic energy initially minus the kinetic energy final minus kinetic energy initial. Okay. That is equal to kinetic energy final is a half mv final minus the kinetic energy initial is a half mv initial squared, both of them, the velocity squared, and this changing kinetic energy. Okay. Now the mass we know is 10 kilograms, so we can actually take out the mass. Okay, a half times the mass we can take out, and we are left with the final velocity squared minus the initial velocity squared, and on this side we have the changing kinetic energy, meaning so 2 times the changing kinetic energy over the mass will give us plus the initial velocity squared plus the initial velocity squared will give us the final velocity squared. Okay, so we have struck upon an equation which we can use to calculate the final velocity. So the final velocity is equal to the square root of the initial velocity squared plus 2 times the kinetic energy over the mass. That will be your final velocity. Let's see. We Let me just fill in at the back there. That's 2 times the kinetic energy of 148, the changing kinetic energy 148 joules over the mass of 10 kilograms plus wait, let me just check my math here. Yes, 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 yes. Okay, seems fine. And the velocity squared, the initial velocity squared, which is 1.5 meters squared. Okay, that should give you an answer of 5 point, if you work it out in the calculator, 5.65 meters per second. Okay, you should get 5.65 meters per second if you work it out that way. Yes, 5.56 meters per second should be your answer. Are there any questions so far? Any questions? If there are no questions, then I would say thank you for joining today. That was our last question for today. I'm going to stay around for 1 more minute. If there are still questions, people asking questions, then I'm going to stop my stream. Uh, See you guys next week and all the best. Okay, Calvin, which part of question 5 do you want me to explain again? Mr. Calvin, which part of question 5 would you like me to explain again? Okay, part 2, the second part of question 5. Okay, the force due to, you want me to explain part 2. Okay, let's see. So you want to know what the force is that, is it only, while I'm preparing, let me just ask, is it only part 2 you want me to explain? Is it only part 2? Okay, remember part 2 asks the following. Calculate the work done. Determine the increase in internal energy of the crate inclined system owing to friction. Basically, the change in kinetic energy due to friction. Okay. Now, the change in internal energy due to friction is just equal to the force of friction multiplied by distance. That's the change in internal energy due to friction. Okay, that's the formula. But in order to use this formula, we need the force of friction and we have the distance. Okay, now the force of friction we can calculate from the normal force. Remember, the normal force, we can calculate the force of friction from the normal force. We know that the force of friction is equal to the coefficient of kinetic friction multiplied by the normal force. Okay, but we have the coefficient of friction, but we do not have the normal force. Okay, so first of all, in order to answer this problem, we will work out the normal force, and then using the normal force we'll calculate friction, and then using friction we'll calculate the change in internal energy. Does that make sense? So in order to calculate the normal force, we calculate, where is my drawing? I'll do with it. Okay, never mind. In order to calculate friction, we work out the normal force. So first we need the normal force, first of all. So the sum of the forces in the y direction is equal to the mass times the acceleration in the y direction. But we know that there is no acceleration in the y direction, so it is zero. But there are forces in the y direction. Okay, there's the normal force in the y direction, and then there is the perpendicular component or the adjacent component of the gravitational force. Remember, this block is at an incline. Okay, gravity is going this way, then it has a horizontal component going that way, that force, that perpendicular force going that way, and then we have the normal force going upwards. Now the y direction is in this direction. Okay, so there are two forces in that direction. Okay, it is this perpendicular force, this perpendicular component of that force, and then there is the normal force. Okay, now the perpendicular component of that force is just equal to the weight, 98 newtons, multiplied by the cosine of the angle there. That angle we've been given as 20.08. Is it the same angle? Yes. 20.08. Okay, is equal to 0. Now if we solve for n, we have that. Oh, so you understand it now. Do I need to continue? Okay, let me just continue it anyway. So that force, and the normal force is then 92.1 newtons. And then using the normal force, we plug it in. So the force of friction is then equal to Force of friction is then equal to 0.4, the coefficient of friction, multiplied by the normal force, 92.1 newtons. That gives us a force of friction of 36.8 newtons. Now, if we have the force of friction, we can calculate the change in internal energy. The change in internal energy is then equal to the force of friction multiplied by the distance. So 36.8 newtons multiplied by 5 meters. And that gives us 184 joules. Okay. So, any more questions? If you have any more questions, just please ask. If there are any more questions, just ask. Otherwise, I will be saying goodbye. If there are no more questions, I will say goodbye and a good week. No more questions.